jokes in the time.
Okay.
I'll have to get some. My brother has just an unending stream of jokes. Of course, some of them I probably shouldn't tell.
We can close the door.
The one I actually remember from the last time we went golfing, I can't tell. So, not to encourage that kind of behavior, but that's just the way my brother is. So,
We're good.
are we back? Okay. So we want two horizontal asymptotes. If you look around the functions that you know, you probably, unless you saw the logistic function somewhere in your life, never saw a function that had two horizontal asymptotes. But if you look at the logistic function, it does. Reason being, as x gets, if x goes off to negative infinity, what's going to happen to this function here? This side over here, if x is going off to negative infinity, that means I'm raising e to large positive numbers. So that's going to be huge. So, well, as this gets really big, I'm dividing a by it, and so this whole fraction here is going to get very small, and I'm going to get very close to d. So I have a horizontal asymptote off as x goes off to negative infinity because I just get closer and closer to d. On the other hand, as x gets very large in the positive direction, just plug in very large positive numbers for x, I get e raised to large negative numbers, which makes it close to 0. So this part's going to be 0, and what am I going to be left with? A plus d. So I have two horizontal asymptotes. One that I get close to as I go off to negative infinity, one I get close to as I go off to positive infinity. So we have here a function that has two horizontal asymptotes, and that matches what some sort of very broad level biology that we've taken looking at this. And so we want to go in and fit a logistic curve to it. The logistic curve isn't there, so we have to do what? Define the function. So we have to type it in, it's a divided by 1 plus e, but e is exp, negative c times x. And it would be better if there was one parenthesis there, plus d.
You forgot the b.
I did forget the b. Thank you. That would be unfortunate. I don't have my glasses on, it's very hard to spell. Alright. So we add logistic to it, we try it. Takes it a little longer to try ones that it hasn't come up with itself. And if we look, does it look like it fits pretty well?
Yes.
And in terms of a measurement of how well it fits, what do we use? Our root mean square error. This gives us a feel for sort of the average error. And that's pretty small. And so there is our function. What can we use that function to do in this particular case? What use would it be?
Predict biomass at later times.
So we can predict the biomass. In particular, we could predict what? What biomass might be of specific interest? See?
Predator-prey models.
Okay, if we had a predator-prey model for this, we could compare against that. See? Good. Other things that would be of. Okay. How about the maximum biomass? What's the largest these things can get? How would I figure out what the largest biomass for an algae bloom is? Yeah, we're looking for the asymptote as x goes off to positive infinity. And in this case, so that would be a plus d, and so we end up with what being our largest possible biomass for one of these algae blooms.
5.3-ish.
Yeah, about 5.3-ish. Questions about
Is there a way to add another like term into that so that it gets even closer? Because the Gaussian actually gave us a closer fit,
Okay.
like based on error. Is there a way to add in another term to the logistic curve so that it can tighten up around the edges?
Not and have it be called logistic. This is the classic logistic function. So you could add some more terms or try some different things with it, but you would be finding new functions and new functions to fit it. It wouldn't be a logistic function anymore. It would be some kind of modification that would get a different name or something like that tacked onto it. So yeah, we could go try modifications. Gaussian, why might we not? What's the problem with a Gaussian? Does anybody even know what a Gaussian is?
Be with like the isotopes.
If you look at, where is Gaussian? There's Gaussian. That formula right there, if you've had statistics, could be familiar.
Yeah, it's
It's a normal distribution. So it's the formula for a normal distribution is what you're getting with a Gaussian. And so it does come, and in terms of the root mean square error, it works better.
We're just gonna go
With a normal distribution, what happens though? So we're seeing it goes up. What's going to happen eventually?
if you expand out, it'll also go back down.
It goes back down.
So if there's like an algae civil war, then
Well, yeah, they sort of pulse, you know, so it pops up and then it gets old and dies. You know, sort of the whole bloom were to do that. You might have a model that Gaussian would fit well with, but here we're just looking at its growth side. And so even though the Gaussian gets closer numerically to our data, the logistic function is a better long-term fit because it models what we expect to happen, which is this thing will grow, reach sort of some sustainable population level, and then just kind of sit there and rejuvenate itself, hit an equilibrium.
Assuming that like the algae was like a cyclic
Mhm.
type thing, I mean, would the Gaussian number work better there? Like if they, certain times of the year would,
Popped up and then went away.
yeah, maybe
Certainly
plot
could.
that against time.
Mhm. We would need more data. We'd need the experiment to actually go over into the regime where the algae population starts to decline, so that we could actually see how that decline happens, to see if a Gaussian is really a good model for over there.
just out of curiosity, what are the units on these things?
And
I didn't pay enough attention.
Days and millimeters.
Other questions about doing an empirical model?
I have a question.
Yeah.
What if for some reason, like in your data points, like we're here, it like actually kind of, you can see it curve off.
Mm-hmm.
What if somehow down the road it actually curves back up again? Could you still fit a logistic function to it? Or
No.
is that,
Well,
for some reason, has that weird dip in it or something?
yeah, if it has a weird dip in it, then the logistic function is going to get off. So if your data is kind of coming and it's looking logistic, but then it does something like that. If you fit a logistic function to it, what will happen is it'll try and split the difference on that dip, and so you'll end up with something that looks like that coming up.
Is that just the problem with modeling real world?
Oh yeah. Or you think there must be something else going on. You look for what caused the second boost here. There might be something going on physically, biologically, that caused that. And so you might have a function that works really well for this first part, but then somehow conditions changed. So different happened. We're actually going to see that when we take a look at the elk population in Yellowstone. And you will see that in 1995, suddenly things changed. And those of you who know this area know what happened in 1995 to make things change. But we'll look back and then you can say, oh, something must have happened here because the dynamics suddenly shifted. And then you go find a different function because you wouldn't expect the same function.
Would you ever split it up into two functions to model their stuff?
Oh, all the time.
I thought that was 1985.
What?
The 5.
Not not talking about the fire, actually.
Talking about the wolf pushback.
Talking about the reintroduction of wolves. And suddenly you had another predator that preyed on the elk population. And then we'll actually take a look at the data for that, play around with that. So, any other questions about conducting an empirical, finding an empirical model, taking a look at it? We're good to go until you try one.
So are we, because in 271 we did a lot of by hand stuff.
Mhm.
Are we going to do more focusing on like using computer applications and then analyzing it and how to change? Okay.
Yeah. The reason we did it by hand in linear algebra is because that's how you actually do it. Is you use linear algebra, you use matrices, just like we did. Since this class is not focused on linear algebra, it's focused on the applications. We'll let the computer do whatever we can get it to do for us. If you want to know how this is actually done, come by my office sometime. I'll be happy to explain it. So, yeah, very few people ever take me up on those. It's really disappointing.
I just have a quick question from the reading.
Sure.
It says that a mathematical model is a concise verbal description of things that impact a system.
Mm-hmm.
When I think of a mathematical anything, I don't think of a verbal anything.
Oh.
So like, why is, why do we call a mathematical model something that's like this spoken description?
Okay. There are several reasons I chose this textbook. One of them is the fact that it's free.
Right.
Which is nice because the actual textbook that they've used in the past for this class costs over $200.
Yeah, thank you.
Yeah, we were disgusted by it as well, so I found this free one. The other reason is this is written by biologists. So what you're going to get, from me, you're going to get a mathematician's point of view on how this works. As you read the book, you're going to get a scientist's viewpoint on the mathematics. So to a scientist, the mathematical model is a statement such as the size of the mold growth is proportional to the amount of time that it's been growing. And that is a mathematical model. And that's how they used them. Now, they used them verbally. Oh, it's proportional to this. Or it's inversely proportional. The amount of light that's in your pond is inversely proportional to the depth of the pond. So that's, when they talk about it being a verbal description, that's the kind of verbal description they're talking about. Basically what they're doing is taking what the equation we would write down, and then as a mathematician I would say it was the equation that was the mathematical model. What they're doing is they're verbalizing the equation. They're saying what the equation tells you. It says, oh, this is proportional to that, or this changes in this way. So, excellent. Other questions about reading?
Are the homework problems posted?
Not yet, but they will be in about 15 minutes. So you'll have all the chapter 1 problems. The ones that will be due next Tuesday are over those first 3 sections that you read. And then next Tuesday, we will start into 2 things. First, Yellowstone is going to let us in for free, so we get to go to Yellowstone.
Yeah.
Which means that on October the 6th, if you possibly can, and I understand that some of you will not be able to because of work obligations or other obligations that you have. But if you possibly can, on October the 6th, we'll be meeting here bright and early at 7 in the morning and jumping into some vans and heading up, and we'll be stopping at several places in Island Park, and then we'll also go into Yellowstone and go around the lower loop in Yellowstone. It's a pretty hefty day. We leave hopefully before 7:30 in the morning, 7:15 in the morning, and we get back around 9 at night. But on the student evaluations every semester for this class, it's the only thing that gets commented on. Other than Brother Cox shouldn't be allowed to teach. But that statement, and then the field trip was great. So we'll be doing that on October the 6th.